You know, we use the internet all day, every single day. It feels totally instant, right? Almost like magic. You click a link and boom, the world just appears on your screen. But have you ever really stopped to think about what's actually happening behind the scenes? What's going on in that split second?
So let's actually do that. Let's follow a single click on its incredible, invisible journey all the way across the globe and back. What really goes down in that tiny fraction of a second after your finger leaves the mouse? Because that one simple click, it doesn't just stay on your device. Oh no, it kicks off this incredibly complex, high-speed conversation between your computer and another one that could be literally thousands of miles away. It's a journey with its own language, its own rules of the road, and its own information superhighways.
Now, probably the best way to wrap your head around this is to think of it like an old-school postal service. See, the internet is built in these layers, and each one has a very specific job. Your browser, that's the application layer, it writes the letter, your request for a web page. Then, the transport layer puts that letter in a secure, trackable envelope. After that, the network layer slaps the full destination address on it. And finally, the link layer acts as the actual mail carrier that starts moving it on its way.
Okay, but for this whole postal system to work, every single computer on the network, from your phone to some massive server in a data center, has to agree on a very strict set of rules. They all have to speak the exact same language. We call these protocols, and they govern the entire journey.
So, rule number 1. We have to figure out where to send our letter. This is the job of something called the DNS, or the Domain Name System. And you can just think of it as the internet's giant global phone book. Its one and only job is to translate the website names that we humans can remember into the long strings of numbers, the IP addresses, that computers actually use to find each other.
And here's what that looks like in the real world. We type in testfire.net, but the DNS immediately looks it up and tells our computer, oh, you actually need to go to 65.61.137.117. I mean, can you imagine having to memorize that for every website you visit? No way. DNS is truly the unsung hero that makes the web usable for all of us.
All right, so we've got the address. But our computer doesn't just start, yelling data out into the void hoping for the best. It's actually very polite. First, it needs to make sure the server on the other end is home, so to speak, and ready to receive the package. That's the job of TCP, the Transmission Control Protocol.
TCP does this with this really elegant little dance called the three-way handshake. First, your computer sends out a little packet called a SYN, which is basically asking, hey, are you there? The server on the other end replies with a SYN-ACK, saying, yep, I'm here and I hear you. Finally, your computer sends one last ACK, which says, awesome, here it comes. All of this happens in milliseconds, and it establishes this rock-solid, reliable connection.
So far, we've talked about all the rules and the language. But where does this journey physically happen? Well, the internet isn't some fluffy cloud in the sky. It is a very real, very tangible network of undersea cables, routers, and these massive buildings where all of these different networks come together.
And right at the heart of this physical network, you'll find these places called Internet Exchange Points, or IXPs for short. These are the actual buildings where different internet service providers physically connect their networks to exchange traffic with each other directly and super efficiently. A really great way to think about an IXP is like a major international airport. But instead of passengers and airlines, you have data packets and networks. And just like an airport, the more networks or airlines that connect to one IXP, the more efficient and valuable it becomes. It's a central hub for data to fly in and out of.
And of course, every airport needs air traffic control, right? Well, for the internet, that system is called BGP, the Border Gateway Protocol. You can think of BGP as the internet's air traffic controller. It's constantly talking to all the other networks, figuring out the best, most efficient paths for your data to travel from its origin to its destination, navigating this unbelievable global web of connections.
But here's the catch. That journey isn't always smooth. BGP is kind of like the internet's GPS, but just like the GPS in your car, sometimes the directions it gives aren't the best. Sometimes the map it's using is constantly and erratically changing.
This is a huge problem known as routing instability. It's when the paths that BGP is recommending are constantly flapping back and forth or just changing without warning. This creates total confusion in the network, and it leads to delays, lost data, and basically the digital equivalent of a massive traffic jam. And this digital turbulence, it really comes from two main sources.
You've got policy-induced instability, which is kind of like two airlines having a business disagreement over whose planes get to fly where. And then there's protocol-induced instability, which is just an inherent part of the system itself reacting to real-world physical events, like a deep-sea cable getting accidentally cut by a ship's anchor.
So, this leads us to a really fascinating question. If we can't always trust the directions the internet gives us, can we at least measure how unreliable they are? If we can somehow quantify the wobble in any given route, maybe we can start choosing better, more stable paths for our data to take.
And this is exactly what a group of researchers set out to do. They developed this metric. They called it phi, but we can just call it a wobble score. The idea is actually pretty simple. Every time a route changes, its score goes up. If the route stays the same, the score slowly ticks back down. So a higher score just means a wobblier, less reliable path.
And wow, when they applied this metric to real-world internet data, the problem became crystal clear. You can see it right here in this graph. That red line shows the maximum wobble score. Those sharp spikes, those are major instability events, times when the internet's GPS is just going haywire for certain routes, and you can see that over time, things just get progressively worse.
But here's where it gets really interesting. Their research uncovered something truly astounding. By analyzing all the possible routes between networks, they found that for about 90% of destinations, a more stable path, a path with a lower wobble score, was actually available than the one BGP was currently choosing.
Now, you might be thinking, okay, but there's got to be a trade-off, right? A more stable path must be a much longer, slower path. Well, this graph shows that's usually not the case at all. See that huge flat section right in the middle? That tells us that for the vast majority of those 90% of routes, we could switch to a more stable option without adding any extra hops or making the journey longer. It's not a choice between stable or fast. We can actually have both.
Just as the researchers concluded in their paper, choosing a more stable path would not come at the detriment of making most of those paths longer. And what that means is that a more reliable, less wobbly internet is actually achievable.
So the big question is, how do we actually implement this? How do we build a network that can use a wobble score to make smarter routing decisions in real time? This is where the story of our little click comes full circle, and we get to look toward the future of the internet itself. And the answer, it turns out, lies in a huge technological shift called software-defined networking, or SDN. The big idea here is to separate the network's brain, all the control logic, from its brawn, the actual physical hardware that moves data around. By centralizing that brain into a single piece of software, the entire network becomes programmable, flexible, and way more intelligent.
And that leaves us with a final, kind of mind-bending thought. If our networks are no longer just rigid boxes and dumb pipes, but are becoming pure, programmable software, what are the limits? Could we build an internet that doesn't just choose the most stable path, but actively anticipates traffic jams and heals itself before we even notice there's a problem? That's the future we're building right now.